All right, so welcome to week 9, day 1 of the game development. We're going to finish our discussion of math today, and we'll obviously do lots of vector stuff throughout the rest of the semester. But today is the last big component of linear algebra you guys need to know. So we already know how to do like scalar times scalar. 2 times 2 is 4. Cool. We know scalar times vector, where you just multiply the scalar. 3 times 4, 5 is equal to 12, 15. So you just multiply the scalar times each component. Pretty easy. We know vector dot vector. It's the inner product, it's called sometimes. And that is x1, x2 plus y1, y2. So that's the dot product. Then there's also vector cross product with vector, which creates a vector pointed orthogonal to the two input vectors. If you're doing the scalar cross product, though, it's x1, y2 minus x2, y1. This is the cross product. And so dot product is used to tell something if one vector or one point is ahead of you or behind you, or if two vectors are looking the same way or looking in opposite directions, or if they're looking at 90 degrees to each other. The cross product is used to tell if something is to your right or if it's to your left. And that's for the scalar cross product. For the vector dot product, for the vector cross product, it gives you a normal vector. So if you contact the surface of a plane, or if you contact the surface of any object, really. So like you got this, vitamin bottle here, and a beam of light hits the surface right here. What you do is you construct a normal plane. In other words, you work out the, like these are triangles. If you zoom in, it'll be a triangle. So the surface of the triangle forms a plane. And so a normal vector to it is a orthogonal vector, a vector sticking straight out of the plane. So whatever direction the plane's in, the normal vector is pointing straight out of it. That's another use of the cross product. It's used for bouncing and for lighting and a lot of things. And so what we're going to learn today is matrices. So a vector is like a 1D array, right? 1, 2, 9, 7, which I'm not reading the numbers on the screen. That would be a vector. A 1D array is a vector. A matrix is a 2D array. So a matrix is something that looks like this. This is a 3x3 matrix. Okay. And every transformation you do in a video game uses what's called a transformation matrix. And these matrices can do different things. They can do translation, and they can do rotation, and they can do scaling, and other things as well, like skewing and stuff like that. The most basic matrix is this one, which is 1s on the diagonals and 0s elsewhere, and this is called the identity. This is the identity matrix, and it does absolutely nothing. So what can we do with a matrix? Well, the most basic thing you can do with a matrix is scalar times matrix. For example, if you took the number 7 and multiplied it by this matrix here, then what you do is you just take the scalar quantity and multiply it across every element here, and you end up with 7, 7, 7, and zeros in the rest. I'm not going to draw the zeros. Do you guys understand? So if you multiply a matrix by just a number, then it just scales it. So all the numbers just, the 1 turns into a 7, the 0 stays a 0 because 0 times 7 is 0. You guys understand? So if you had a more complicated matrix like 2, 2, 7, you multiplied that by 7, you would end up getting 14, 14, 49. It's like multiplying a scalar times a matrix. You just take whatever scalar you're multiplying in, and every element in the matrix gets multiplied by. So, okay, let's do an example then. So let's say you've got a matrix 4, 5, negative 10, 16, 3, 7, 12, 2, and 0. Okay, so Haberin, let's say you're going to multiply 10 times this matrix here. This is going to give you another 3 by 3 matrix. Ten times each number in the matrix. Yes, exactly. So what is the top left number going to be? 40? Yep. And what is the top middle? Top right? That's a negative 10. Negative 100. Negative 10 times 10 is negative 100, right? Okay. 16 times 10 is what? Lavi, what's the middle number? Lavi, you here? Collins? Oh, no, middle number. The middle number, Lavi. This one. Collins, what is the middle number going to be? The middle number. This one right here. Collins, you here? Sorry, what's up? What is the middle number going to be here? That number right there. We're multiplying a matrix times 10. So all of the elements of the matrix get multiplied by 10. So 3 times 10 is 30. Very good. 70, 120, 20, 0. Okay. So you guys all got that? Scalar times matrix. Cool. All right. So now we get to the fun bits. This is the only part of the linear algebra that you have to pay attention. It's like traditional multiplication. Yep, exactly. Just like scalar times matrix. Scalar times vector. Each element of the vector gets multiplied by the number. Okay, so now let's do vertex. Why do I want to keep saying vertex? Vector. Probably because matrix. Vector times matrix. Okay. So when you do a vector times a matrix, we typically draw the matrix on the left. Let's do 7, negative 8. Typically draw the matrix on the left, and we're going to multiply this by 10, 12, 2, and 1. Okay. So how do we multiply a vector times a matrix? There is a couple different ways of describing how to do this. The way that always made sense to me was you take this. Let's see if I can make some room here. You take the vector, turn it sideways, so it becomes 12, 2, and 1, and you multiply it down across the matrix. 1, 1, 1, 7, negative 8. You multiply down and you add across. What does that mean? So you do a scalar multiplication of 12 times all the elements in this vector. So that vector turns into 12, 0, 0. You do a scalar multiplication of that number times this vector here. That turns into 0, 2, 0. And you multiply 1 times these, which doesn't change anything. And we get 7, 8, 1. And then you add across. So you add all the numbers this way. 12 plus 7 is 19. 2 plus 8 is 10. 0 plus 0 plus 1 is 1. Okay. So step 1, multiply down. Step 2, add across. Okay. So basically what you do when you multiply a vector times a matrix is you turn the vector on its side and you treat it as a scalar times vector multiplication for each of the columns. And then you add all the columns together. So when you do a vector times a matrix, you actually end up getting a vector, right? So a vector times a matrix gives you a vector. Let's do an example. So what does this mean, by the way? So this, you might look at this thing and be like, what's going on here? This looks like the identity matrix, except these two guys here are different. So do you remember how I told you that matrices can be used to do transformations? They can be used to do translation, rotation, and scaling. This matrix here is actually a translation matrix. So this matrix here to the right here, in English, if I had to describe this matrix in English, means translate. It's hard to read. If I had to describe this in English, let's pick a different color maybe. Light blue, sure. This vector here means translate plus 7 in the x direction and minus 8 in the y direction. So we have here an input point. This is x, this is y. And then this is nothing. It's always just going to be 1. So if we have a Cartesian coordinate and we got x is 12 and y is 2, what this is going to do is translate the, that should be negative 8, shouldn't it? It should be negative 6. Negative 6. Okay. So if we want to translate this point, do you guys remember how we did translations before? If we want to translate this point 7 to the right in the x direction and 8 down in the y direction, this matrix represents that mathematically. So you always start with the identity matrix, and then you can layer different transformations on top of it. If you want to scale it, if you want to rotate it, if you want to translate it, all of those things can composite together to form a single 3x3 matrix that will do maybe nothing. If it's the identity matrix, it does absolutely nothing. If it's a translation matrix, it will have 2 numbers right here, and this indicates how far to move in the x direction, how far to move in the y direction. If you do scaling, these numbers will change here. If you do rotation, these will become sines and cosines of the angle. And so that's what our topic of lecture is today. And what's really neat about it is that you can actually, rather than having to do transformation after transformation, let's say you take a point and you move it 5 to the right, you move it 5 to the right again. You don't have to do both vector times matrix, vector times matrix. You can composite the two matrices together and just have one transformation matrix at the end of the day. That's why in Unreal Engine you see the translate, the rotate, and the scale on the details panel. All of that is actually just a 4x4, because it's 3D, this is 2D, a 4x4 matrix, and it just pulls the numbers out of it and says this is how much it's rotating around the x axis, this is how much it's rotating around the y axis, this is how much it's rotating around the z axis, This is the translation, the x, y, and z. This is the scaling in the x, y, and z. And it just pulls, it's just a 4x4 matrix. That's all it's holding. And it will place it in the world and rotate it and scale it at that level. So what we had here as input is x is equal to 12, y is equal to 2. After we transform it by this matrix, we end up getting x is equal to 19 and y is equal to -6. Okay, and so you guys see how this matrix, when we multiply down, added across, we ended up adding 7 to x and we added -8. I forgot that the first time. Let's put a negative there. We translated y in the negative direction, and so this will move 7 to the right and 8 down. So it moved from 12, 2 to 19, -6. Questions? I haven't shown you guys how to do scale or rotate yet, just translate. So let me give you a matrix, and just by looking at it, tell me what you think it's doing. What do you guys think this transformation matrix is doing? So it's not starting at 4, 5. It is translating whatever vector you pass in here. You pass in an x location, a y location, and 1. After you do this transformation, you will end up with x plus 4, y plus 5, and 1. Okay. So whatever value we have here, if we had 10, 20, and 1, we'd end up with 14, 25, and 1. Looking left. I don't know what that means. Am I looking left? I don't know. All right, Maine, you want to do the next one? Maine, are you here? Good. All right. So Maine, we will just put in 1, 1, 1, 0, 0, 0, 0. -10, -20 times 31, 41, and 1. All right, so main, first step is you turn the vector on its side, 31, 41, 1, and you will multiply down and add across. So multiply 31 times each of these elements here. What do you get? X minus 310. We're doing the matrix multiplication. We're doing it step by step. So multiply 31 times each one of these elements here separately. Hey, Brent, I don't know what you're asking. What is this? I was asking, what does this matrix do? What kind of transformation matrix is it? It's a transformation matrix that moves whatever point you pass in. The output will be 4 to the right and 5 up. So 310, 0, 0. No, 31 times 1 is 31. So it's going to be 31, 0, 0 for the leftmost column. And then for the next column, multiply 41 times each of these elements. Main. Multiply 41 times each of these elements. Each element separately. 0, 41, 0. That is correct. And then for the last one, Multiply 1 times negative 10, negative 20, and 1. What do we got? Negative 10, negative 20, and 1. Very good. Negative 20 and 1. Now you're going to add across, and so you're going to add all of these numbers together. 31 plus 0 plus negative 10. What do you get? 31 plus 0 plus negative 10. What do you get? (21). 0 plus 41 plus negative 20. Add these across. What do you get? 0 plus 41 plus negative 20 is also 21. And then 0 plus 0 plus 1 is 1. And so with an input of 31, 41, 0, the output becomes 21, 21, 1. Or 31, 41, 1. The output becomes 21, 21, 1. And so that's because it translates this negative 10 in the x direction and translates at negative 20 in the y direction. That's what this transformation matrix means. And so if you pass in 31, 41, it translates at 10 left and 20 down and ends up at 21, 21. Okay. So this is a translation matrix. This translates, in English, translate the point by negative 10, negative 20. That is an English description of that matrix right there. Okay, so let's do rotation. So, okay. What is the cosine of 90 degrees? You have to know a little bit of trig. What is the cosine of 90 degrees? What is the sine of 90 degrees? Okay. So cosine looks like this, right? It starts at 1, crosses to 0, goes. That's a really ugly cosine, but whatever. So at 0 degrees and at 360 degrees, it is at 1. At 180 degrees, it is at negative 1. So at 90 and at 270, it is at 0. Okay. So the equation for doing a rotation is the top left number is the cosine of theta. Consult the cheat sheet. It's cosine, yeah, cosine, theta, sine theta, and negative sine of theta. Okay. So that is how you rotate something. You just plug the numbers in there. So cosine of theta is 0 because we're going to be rotating at 90 degrees around the origin. So this is going to turn into the following matrix. Cosine of 90, 0. Cosine of 90, 0. Sine of 90, 1. Negative sine of 90, negative 1. Okay. We're not going to translate it. And so this is in English. Rotate the point 90 degrees. It would be counterclockwise around the origin. Okay, that's what this means. So if we were to take as an input point, let's say 10, 20, and 1. Turn it sideways, multiply down, add across. What do we get? Hey, Bryn, you want to do this one? It says rotate the point 90 degrees counterclockwise. Or, as the Brits call it, anti-clockwise. Anti-clock. It's too big. 90 degrees Widdershins. Sorry, what was the question? Yes. So we wish to do this multiplication here. So in order to do so, we take the vector, turn it sideways, 1021. You turn it sideways. You got your matrix here. 0, -1, 0. 0, 1, 0, 1, 0, 1. So let's do it one column at a time. So multiply 10 times each of these elements separately. 10 times 0, 10 times -1. Okay. So what do we get for the first column? 0, followed by -10, followed by 0. Okay, second column, 20 times 1 is 20. 20 times 0 is 0. 20 times 0 is 0. Third column, 1 times 0, 0, and 1. Okay, so that's step 1. Remember to do vector times matrix. There's 2 steps. First step is multiply down. Second step is to add across. So you're going to add each of these rows. 0 plus 20 plus 0 is 20. -20 plus 0 plus 0 is -20. 0 plus 0 plus 1 is 1. So we have ended up with 20, -21. So our input point was, this is x, right? This is y. This is nothing. Right? It's not z. It's nothing. It's always just going to be 1 under normal circumstances. That's going to be x. That's going to be y. So, so our input point was x is equal to 10, y is equal to 20. And then we rotated it 90 degrees counterclockwise. Oh, no, this is clockwise. Sorry. Clockwise rotation. My bad. We'll fix it in post. There we go. All right, so there. Okay, so it's clockwise rotation. And so we ended up with x is equal to, so before x was 10, y was 20. Afterwards, x is going to be 20. Y is equal to, did we do this wrong? We did this wrong. That's a 1, isn't it? So it happens you can't read your own handwriting, huh? -10. There we go. -10. -10. There we go. And so x is equal to 20, y is equal to -10. And so you can see the point rotated here. Now if we did it again, it would rotate this way and be at -10, -10, -20. If we did it again, it'd be at -20, +10. And if we did it again, we'd be back where we started. So that is a rotation matrix. And so the equation for a rotation matrix is it's the cosine. Should use a thinner pen. It's the cosine of theta, cosine of theta, sine of theta, negative sine of theta. 0, 0, 0, 0, 1. So that is what a rotation matrix looks like. Now, this is in your notes. You don't have to write this down. And so whatever angle you want to rotate it by, you plug it. Theta is, of course, an angle. You rotate it by clockwise, not anti-clockwise. So theta is the angle you rotate it by clockwise, and then that gives you these numbers here. So cosine of 90 is 0. If you did, if you wanted to rotate it 180 degrees, what would that look like? And let's pick on Collins. So Collins, give me a rotation matrix that will rotate the point 180 degrees counterclockwise. It's the same as clockwise. So Collins, fill in the 4 blanks there on the screen. Collins, you there? Sorry, I'm having connection troubles. Okay, so I can make my text bigger if you want. Cosine of theta, sine of theta, negative sine of theta, cosine of theta. So do you remember what the cosine of 180 is? Cosine, it looks like this. Positive 1, negative 1 at 180. Yeah, so the top left corner is going to be negative 1. And what is the sine of 180? Sine looks like that. So at 180, it is 0. So the sine of theta is 0. What is negative 0? Well, negative 0 is just 0. And then cosine of theta, we already know that one. And so that is a rotation matrix to rotate a point negative 180 degrees. So if you put in x is equal to 10, y is equal to 20, multiply it down, add across, you end up with negative 10 and negative 20. So it's a mirror image. Okay. Makes sense? And an experienced game developer can just look at a matrix like that and see what's going on. In Unreal Engine, all the math is actually done for you. You just drag things around in the blueprints and say multiply this times this, and it does the actual number crunching for you. But you still have to kind of understand what's going on. Especially like you'll be dealing with like rotators and stuff. Like, look at, given two positions, rotate me to face towards the target. Right. It's a very common thing. Okay. Windows Calculator no longer has sine and cosine. Sure does. It's just under scientific mode. So there's a standard mode, but if you switch over to scientific, you can see that there is sine, cosine under the trig dropdown here. Okay. So what is the transform we have not done yet? We've done translate, we've done rotate. Which one have we not done? Scale. Good. So scale looks like this. Not like that. Like this. Yeah. There we go. So this will scale this point times 5 away from the origin. So if we're at x is equal to 10, y is equal to 20, 10, 20, here. If we were to scale this 5 times away from the origin, it'll be like way up here, right? And turn it sideways, multiply it down, add across, we will end up with 50, 100, and 1. You guys see that? 10 times 5 is 50, 50 plus 0 plus 0 is 50, 20 times 5 is 100, 100 plus 0 plus 0 is 100, and then 1 is 1. Yep, pretty easy. Pretty easy. So, yeah, you just look at that and you're like, that's a scale. Mm-hmm. That's a scale, all right. So, can you combine them together? Yep, you can. And so if you do something like this, negative 5, 1, 0, 0, 0, 0, 0, and you multiply that by 10, 20, 1, you are going to end up with negative 50, negative 100, and 1. So which two operations did I combine here? So if the input point is 10, 20, the output point is negative 50, negative 100, I'm doing two different operations. What are they? Input of 10, 20. So it's being moved 5 times away from the origin, and it's being rotated negative 180 degrees or positive 180 degrees, because it literally is the same thing. And so it is, I should draw a line coming out exactly in the opposite direction like this. So it is doing, what is it, negative 50, negative 100, down here somewhere. So it is doing 180 degrees rotation and scaling at the same time. It's rotation and scaling. Okay. So all of these things composite together, right? That's a times 5 scale. That's a 180 degree rotate. Look, they're just, it's just one matrix that does both. So rather than having to do a rotate, then a scale, it's just all at the same time. Okay. And computers are highly optimized to do this form of matrix math, of multiplying and adding. So there's specific instructions to do fused multiply adds like that are very, very fast, oftentimes optimized for exactly 4 numbers, for the reason that in 3D games, a 3D point needs a 4x4 matrix. Just like a 2D point needs a 3x3 matrix. A 3D point needs a 4x4 matrix. Okay. And this is always 1. Okay. And that's always 1. Under normal operations. There are tricky things you can do, like all sorts of weird things you can do, but under normal operations, those are always 1. So can we do a translate also? Sure, let's try it. Okay, so let's draw another one, whatever. Bits are free. Okay, just by looking at it, what is this transformation matrix going to do? If you just have to guess. Just had to guess. What 2 transformation operations is it doing? Yep. Hebron, you're correct. It is doing a translate. It's going to move it 3 in the x direction and 4 in the y direction. And it's doing a rotate. This is a rotation by how many degrees? (270) or negative 90, either way. So if we have as our input point 10, 2, and 1, and we multiply it down, add across, we end up getting 2 times that is negative 2, plus 3 is 1, and that is 10 plus 4 is 14. So rotated from 10, 2, it rotated left 90 degrees to be, would that be negative 2, positive 10. And then it moved 3 to the right to become 1 and 4 up. So it moved from negative 2 comma 10 to be 1 comma 14. So it did the rotation first, then the translation. Okay. So this is a rotate by negative 90 degrees, then a plus 3, plus 4 translate. The order is important. Yeah. It is. Okay. It is a rotate then translate. If you translate first then rotate it, you get a completely different number. Okay. And so let's just mix it up a little bit more and just turn this into a 2 and turn that into a 2. Now what operations are we doing? What do you think? If I do the math here. So we're doing all of them. Yeah, we're doing a scale. We're doing a scale and a rotate at the same time. It doesn't really matter which order you say these. It does the scale and rotate first, then it does the translate. And so it is starting here, and it is rotating to -2 times 10, doubled out to like -420, -420, and then it's moving northeast from -420 by 3/4, so that turns into -124. Kind of. Okay. So it's rotating and scaling, and then it translates after. And there you go. That's about all you need to know. Maybe we'll do matrix times matrix at another point. But this is the most important thing, because all these different operations you do ultimately boil down usually to a vector being multiplied by a matrix, and you get a resultant vector. That's why it's a transformation. You have an input vector, it goes into the transformation, and it comes out as gold on the other side. Wait, that's a different thing. That's alchemy. You take an input vector, and you get an output vector, and the transformation matrix will translate it, or rotate it, or scale it, or all three, or two of them. Yeah. Okay, so that is that. Can you do the math? Can you multiply down, add across? That's the math skill. It is both multiplication and addition. It's very advanced stuff. Okay. Being slightly mocking, but like I said, nothing in this class requires higher than a trig, I guess. There's a little bit of trig in this, but it's mostly just multiplying and adding things. Okay, so let's go into Unreal Engine. All right, so let's see. It's free for this month. Free for the month. Let's see what we can pick up here. Hack and slash FX. That looks cool. Medieval Castle Modular. Ooh, that's nice. Office scene. I don't really care about offices, but maybe. Advanced vehicle system. All right. Ooh, $80 normally. Nice. Turn-based RPG template. $75 normally. It's got 18 whole reviews. The person who made this has made, I don't know, $1,000 minus whatever Unreal's cut is. All right, so let's go and acquire some free stuff here. Check out. I thought you were really asking about what? Yeah, no, I was. Like, can you do it? Because, like, there's 2 steps. Let's multiply down, add across. Just have to make sure if you understand that, you can do it. All right, so let's go ahead and launch our thing. And let's continue our discussion of blueprints, I guess. That's kind of important. How do you interact with the world? Because ultimately, we've done a lot of stuff with landscaping and materials, but that's not really interactive. That's like it's like art. You know what I mean? Like art, and we'll probably do animation as well. I've been messing with animations, and we'll probably do some animation as well. The yeah, this you'll see something that my IS-50 B students asked for, which was procedurally generating things. So it's dynamically creating sculptures in real time. Alien sculptures. They randomly grow in a random direction, and after 30 seconds they go away. So kind of fun, kind of neat. That's IS-50B, so don't worry about that. Okay, so how can you interact with the world? Right? Let's say I'm making just your standard Quake, Overwatch, Call of Duty, boring first-person shooter. Although, Quakes, they're not boring, but you know what I mean? Like, let's say you're making a first-person shooter. How do you have the world interact with the player? Now, I'm not talking about you, the player, interacting with like the mouse and the keyboard. We'll probably talk about that, actually. How to do keybinds and events and mouse clicks and stuff like that. But I mean, you got a player in the world, right? And I'm going to be like shooting at people and stuff, right? Why is that ball coming out of my... It's weird. How do players interact with the world? I'm asking you guys. Like, you guys have all played video games, I hope. Like, how do you have things in the world interact with each other? There's only a couple different ways, really. Physics. Okay, so you can have one object collide with another one, and when they collide, then some sort of physics interaction takes place. You get the mass or density or volume, of one object and the other object, and you figure out, and usually the physics engine handles that for you, right? So physics would fall under like touch, right? So one object touches another object, right? Okay. What else? So one way an object, an actor in a world, an actor is anything that can move within the world. The only way, feasibly you could have gravity, I guess, but usually the only way that they interact through physics is through touching each other, right? What else? How else can, you got two players in Team Fortress, Call of Duty. How do they interact with each other? What are the different ways in which they can interact? Emotes? Okay. Yeah. They could chat, I guess. Sure, but I mean like in the game itself. Right? How do you, shooting? Yeah. What kind of shooting? Tell me about shooting.
Can I go play Skyrim?
Can you play Skyrim? Yes.
What are you teaching them?
I'm teaching them how different things in a game. Like, yeah, let's talk about Skyrim. So you're the Dragonborn, right? Spoilers, but you're the Dragonborn.
Oh yeah, when I killed a dragon, its bones kept wiggling and shaking like it was still
Ragdoll physics, never good. They really should despawn. They really should despawn the dragons after a while.
Just like those cultists. Since I had the DLC, there were cultists came to Whiterun.
Mm-hmm. And murdering you.
And when I killed them, the bodies were left in front of this house. I tried to go into it, but it's like, no, you must have the key to go into this house. And I realized that's the house that I was going to buy to live in. Whiterun, and I'm like, why these bodies? So I picked it up and like moved it out because before I didn't know how to do it.
Yeah, so let's say you're playing Skyrim and you want to have the Dragonborn, the character in the game, interact with the world. You can talk to people, that's one thing. So how do you talk to people? You hit a talk button or something, X, right? Hit X, and then what happens? How do you actually talk to somebody in the world? How does that happen? Like how far away can you talk to somebody? Like who do you talk to? Some random person in the world? How does that happen? What happens when you walk up to them? Okay, so you have to be within a certain these things have collision turned off. That's right. I was messing with these barrels. Collision. Here. Collision presets. Default. Save. Compile. Close. Play. There we go. So there's different spawn points for these barrels in the world. And let's see over here, we got the rapids, and they've got barrels racing down the water now. So yeah, so you walk up to somebody, and yeah, okay, so sometimes, yeah, that's good. So sometimes you're just walking next to a guard, and the guard says, hey, you seem to be good with that destruction magic. Maybe you should not burn the city down, which is hilarious because you can't burn the city down. Skyrim is not that interactive. So yeah, you can walk up to them. They can call you. They can randomly call out to you. So there's different ways to interact in the world. How do you shoot people, right? So Stafford says, there's melee, there's projectiles, and there's hit scan. Okay, and melee and hit scans pretty much the same thing, right? It's just a short range hit scan, right? If you have a knife, and you walk in behind someone, you click, you stab them, right? It's a hit scan attack. It's not actually anything different. It's just short range, right? And so really, there's two ways of a actor in a world. Maybe 3 ways. We'll say 3 ways. There's 3 ways of an actor in a world interacting with other actors in the world, right? You click the mouse button to shoot. What happens? Do you create a projectile? Do you do a hit scan? Or do you do some sort of radius, like you set off a grenade or something, right, and it explodes around you? That's really it. Those are your basic tools. And this is something I hope all of you guys are like recording into your memory. Those are really the 3 tools you have for one object, one actor in a 3D game to interact with another object. When you go up and hit use on a button, it's doing a hit scan, and it shoots out an invisible line from your eyeball, and it contacts the button. When you hit the use button, it does a hit scan. It's just not an attack. It's just a hit scan. And the Traceline touch the button, activate the button, it pushes on the button, and then that causes the door to open, something like that. Okay, so that's one option. You shoot out an invisible line. Option 2, you create a projectile. You click a button, and a yellow ball, flies out from your gun, right? You create some sort of projectile, and the projectile will interact with the world, and it will eventually touch something. So that's option 2. Create a projectile or touch. Same thing, really. You could touch something directly. You could walk up and bump into a guard with your nose, and if the guard has been properly programmed, it'll be like, "What's that?" And it'll turn around and, "Oh, look, there's a thief," and they'll attack you. And so Traceline is one, touch is another. And the third thing is radius. And so that's like you're walking past a guard. The guard will occasionally do a radius search and see if there's anything within its immediate vicinity that it needs to care about. If there's a dead body, it'll look over and go, "Oh, there's a dead body." Big radius search, is there a dragon nearby? Yes, there is, right? Did the dragonborn just kill somebody? You know, it's those are your three basic tools: is touch, trace, and radius. You know, and setting up a timer to think. You know, so that periodically a guard will, you know, rotate around, look around, do a dot product, you know, to see if it can find anything. Those are your basic tools. That's it. That's really about it. So, if you guys are ready, we can learn how to do those right now. Okay. So these are the fundamentals of game development. This is IS-50A. We are learning the fundamentals, and as it turns out, they're the only mentals. Can a player use a bazooka? Sure. So I can make it so that I click, and it creates a projectile, and the projectile travels through the air. And when the projectile touches something, then it explodes, and it does a radius search. And it finds everybody within a radius, and it deals damage to them based on how close they are to the projectile. That's your standard rocket launcher. The standard rocket launcher creates a projectile that when the projectile touches anything solid, it removes itself, does a radius search around the point of contact, and deals damage with fall off based on how close they are to the impact point. And if the thing actually impacted like a player, they might take extra damage on top of that. Okay. So which one would you guys like to see first? Creating a projectile, touching something, or Traceline? What do you guys feel like? Do you want to see this in PowerPoint form? I do have it in PowerPoint form. It's a PowerPoint presentation called Interacting with the World. Okay. Okay. So if you're making some sort of intelligent agent in the game, like a demon or a spaceship or something like that, you can have an event tick on it that fires off every frame. And we talked last time about why that's a bad idea. A better idea is to create a timer, right? So you create a timer that's like you prime a grenade, pull the pin. So that would probably create a timer that says in 3 seconds, call this function, and that function will do the explosion. That's a lot faster. That's a lot better than doing every tick. Is it ready to explode? No. Is it ready to explode? No. Is it ready to explode? No. Better create a timer, throw it, and then 3 seconds later the thing blows up. Okay. So touch and think are, how you program intelligent agents. So you can have it set to think once every 3 seconds, once every second, once every 2 seconds. It depends. It depends on your budget, how many AIs you have in the world at once. You want to probably lower how often they think if you have a lot of people. But basically with touching and thinking, you can program a guard, and the guard will walk around. And if it encounters the player, it'll be like, oh, halt, Otherwise, it might pathfind from one place to another, and every third of a second it wakes up, does a cone, does that dot product, sees if the player's in front of them. If they are, halt, wait, you're not supposed to be here. And you activate some sort of combat or something like that. And if it doesn't see anything, it goes back to sleep for another half second or so. And so periodically the guard will just wake up and look around and go back to sleep. Essentially, you don't see that in the game, but that's what's happening behind the scenes, and you can do that to keep your CPU performance under control, especially if you have a lot of actors on the scene. Okay. And so if you want to make a rocket launcher, then you create a rocket with a certain position at the tip of your gun, with a certain velocity and the direction you're looking, times the speed. So the direction is the direction you're looking. The speed is 800 centimeters a second, whatever. And you multiply the scalar times the vector, and that gives you the velocity vector of the rocket. And maybe you tell it to think. After 5 seconds, it should remove itself, because if a rocket has not impacted anything after 5 seconds, it's probably not going to hit anything, and delete it so it doesn't spam the world. Otherwise, if it touches something, then you remove it and you do an explosion. And so this model of touch and think and Traceline is basically how you make things in a game. That's how you make a game. That's the fundamental part of a game, is you make these actors that are intelligent, that do things, and they interact with other things in a game. That's what you do when you're making a video game. So you make an actor, they live for a while, they get destroyed. Okay. You technically don't have to destroy an actor, but if you keep making actors and not destroying them, then your frame rate will be terrible. Okay. So, yeah. So, no response on Discord. What do you guys want to learn? What do you want to learn? There's a couple different things we talked about there. You want to learn how to do a trace line? Like how to draw a line from your camera to a point in the world and interact with it? Hit scan weapons, hitting use on a button. Yeah, okay. Because there's only a few ways you can interact, and we've kind of gone over like some of them, right? Like the frosty thing here. Like if you enter the sphere of the sphere collision, it says, "Hey, how you doing?" Plays bird chirping, whatever. We've done our chair guard here, which I really should replace with the real model of the actor, which will yell halt if you move in front of it, right? And so that's a periodic. It periodically wakes up, sees if the player's in front of them. If they're in front of them, they yell halt. So you kind of already know that. So let's do a trace line, and let's see how that looks. Okay, so what do we want to do here? I guess this would be on the player. So rather than creating a ball, and I don't know why that's broken anyway. So rather than creating a ball, we're gonna do a hit scan weapon. Okay, you guys with me? Oh, Dolan's here. Cool. Good to see you, stuff. All right. So those timed interactions, like in Two Souls, yes, yeah. So, so we're gonna click the mouse, and we're gonna shoot an invisible beam out, and wherever it hits the ground, we'll have it burst into flames. So we have like a laser flamethrower? I don't know, whatever. So in order to do this, come into the blueprints folder in the first person blueprints. And it's in that one. Okay, that's just the mesh and stuff, the animations. So there is the blueprints folder inside of first person blueprints. And we are going to come into first person character. And so this is the blueprint that governs input, right? So if you have input axis turn, input axis look up, this handles the x-axis for your mouse, the y-axis for your mouse. And so it's pretty simple. It just passes it on to the controller. The controller is the thing that controls the player in the game. So it just passes the input on. If you hit space to jump, then it will call jump, and if you release it, it stops jumping. Very exciting stuff there. But what we're interested in right now is input action fire and input touch if you're using a touch device, which we are not. We are PC gamers. And so I'm just going to come through here and maybe delete everything. Maybe I'm going to delete everything. I don't know. Do I want the montage play? Maybe. So right now when I click, it plays an animation with a gun going like this. I think I'm just going to pull all of this out though. I'm going to just select all of these guys here. And I'm going to just move that out here. And I'm going to say what happens when the player clicks fire. Okay. So I'm going to drag out from here. And I'm going to search for trace. Okay. And in Quake, it's called trace line. In Unreal Engine, it's called line trace. I don't know why, but there you go. So we are going to line trace, and we're going to line trace by channel. Okay. That works. Okay, so you'll see that this is the reason why I'm teaching you guys about it now, halfway through the semester, is because it requires linear algebra. Look, it requires a starting position and an ending position. So you need to have some point somewhere in the world where the line trace is going to start. Okay? And it should start at the tip of our gun. right? We don't want it to start within us because then it might hit us, right? Burst into flames if you hit yourself. So we're going to start at the tip of the gun. And as it turns out, we have a variable called gun offset that will help us with that. Or we can just copy what we have here. So this is going to, this is getting the end of the gun here. So it's going to get the world location. Okay. So where should the trace line start? The trace line should start at the end of the gun, which is actually that spot right there. So I come over into the viewport, you can see what's highlighted there. When I click on sphere, you see how we dragged out there's a sphere. A sphere is just a point. And so you can just attach points to different parts of the character. And we're a headless pair of arms, by the way. There's no body to the character. All there is a camera and a couple arms attached to it. So you see how there's a sphere? A sphere is just a point, and it's attached right at the very tip of the gun. So that's useful. So we can actually just grab that point, and that will be the place where our trace line will start from. Okay. So we're going to drag out sphere, and we're going to drag. I wonder if we can just connect it this way. Will it get the location? Nope. So we're going to have to get the world location of the tip of our gun. And that is where the laser is going to start from. Now, where is the laser going to end? How do we do that? So if we're shooting a laser, the starting point of the laser is going to be here, right in front of us. But the ending point is going to be the direction we're looking in, and I don't know what the range is, but say a range of like 1,000 or something. Right? So how do we do that? How do we figure out where the ending point is going to be? What do you guys think? The starting point might be at 10, 20, 30, and if we're looking due right, the ending point would be like 1,000, 10, 20, 30. Right? So we have to use the direction we're looking times whatever the range is. So we should create a variable called range. And that'll be the range that'll be a float. And that'll be the range in centimeters that the thing is. Tooltip. Range in centimeters for our laser. Okay. And this will be, I don't know, to make it a really long range, 2,000, something like that. Okay. So how do we get the direction that we're looking? What do you guys think? How do we get the direction that the camera's looking? Drag us out, okay. First person camera, that's the direction that's our camera, right? So how do we get the direction we're looking out of that? Get forward vector. Yeah, so if you want to know if somebody's in front of us, Dawn, you're on the right track. If you want to know if something's in front of us, we dot producted it with the forward vector. So the forward vector is the way we're looking, and if their position is ahead of us, we take their position minus our position and dot product it with the forward vector, and that tells us if they're in front of us or not. But just the forward vector is all we're looking for right now. So the forward vector, that's the direction the laser is going to be going in. And so by default, this is a normal vector, a normalized vector. It's unit. It's one side, magnitude 1. And so if we use this right now, our laser would have a range of 1 centimeter, which is not what we want. We need to scale it. We need to multiply it by range. So we're going to drag this out here, get range, and we are going to multiply it times the vector. So the direction we're looking times the range will give us a vector of magnitude, what was it, 20,000 or something, pointed in the direction we're looking. And so by default, though, this is going to be coming out of origin, the 0. So we need to translate it over to where we are. And so in order to do that, we translate it by adding it to the start position. And that will give us an ending position. So the start position is the tip of our gun. The ending position is the tip of our gun plus the direction we're looking times 20,000. And so that will start from here, go out in that direction, and Traceline will return the first actor. Well, it's going to return a hit structure, but it's going to return the first actor that line contacts. And so this is used for things like you press X to talk to an NPC. When you press X, it sends out a trace line from your camera. The first actor it encounters, that's who you interact with. Greetings, I used to be an adventurer like you until I take a near in my knees. Shut up. All right. You can choose to ignore yourself. So if your trace line is hitting yourself, you can actually pass yourself to the to actors to ignore, so we'll go right through you. You don't need to because there's already a boolean for that. So, but if you wanted to, like if you had a familiar that's flying around and you wanted to pass through, you can pass that in there. Trace complex. Now we'll just do simplified. Trace channel visibility. Yeah, sure. Down arrow. Draw time 5 seconds. Trace color of red. Trace hit color of red, green. Yeah. So we want it to draw a draw debug type. Here we go. We want to draw it for the duration. So for 5 seconds, we're going to click, and then for 5 seconds, it will leave a red line in the world. This is used for debugging. But if you screw up the vector math, you will see your lines coming out of the origin of the world, or it's coming out of like something wrong. And so usually when you do trace lines, you turn on debugging. And so you can literally see where your laser is starting, where it's ending, if the range looks correct to you, things like that. And if it hits something, it draws a little green dot there as well. Okay, so this is going to draw a line in the world. In fact, we can just stop here and try it out. So let's come in here and hit play. And maybe make the screen a little bigger. All right. And so you can see when I click, it is shooting a line from the camera, and it hit something here, and it passed through on the other side there. So that's the first point of contact, and then this is where the line continued and would have hit if it had not been occluded by the box or whatever. Okay. So every time I click, it's doing a trace line, and I have it set to draw the lines for 4 seconds, and so you wait for 4 seconds, and all the lines will go away. It's useful to leave it out there for a while so you can actually look at it from the side and make sure that the origin is actually where you thought it was, right? So you could have it clear immediately, but I actually like leaving them out so you can take a gander at it and see if it's intersecting with things the way that you thought it was. Okay. Now get world direction. Oh no. No, you're all good. You're all good. All right. So what do you guys think of that so far? So do you see kind of the idea of what we're getting at here, of like how you can interact with the world? These things are normally invisible, but that, you hit X, use, or if you're in StarCraft, you click on a space, then it draws a line from the ceiling downwards, and the first unit it hits, it selects it. Do you guys see how this is like amazingly useful? Like beyond useful. There's other options, right? You don't have to do just a line trace. There's other traces as well. So there's capsule trace, box trace. So box trace takes a box and pushes it through the world. Very useful if you want to know if there's like an opening that you could walk through. Capsule, especially if you're a person, people are represented by capsules, which are like rounded cylinders. And so like if you want to know if there's enough room for a bot to like walk down a corridor, you do a capsule trace, which will take that cylinder and slide it through the world like this and return the first thing that it hits. And so if it's open, then you're like, okay, there's a path that way. Right? Multi-box, if one box is not good enough, it's a box, but it can hit multiple things. Sorry. Multi-capsule, again, it sweeps a capsule through the world and it returns everything that area hit. And you can do a sphere trace. And so a sphere will take a sphere, and you can get everything within a radius. Very useful, like I was talking about. You do a rocket explosion, you want to find out who's within the sphere. Useful stuff. So line trace is kind of my go-to, for hit scan weapons, hitting U's, clicking. Typically, I just draw a line out. So what do we do with it? What do we get from a line trace? What is our result value? What you get is a hit result structure, and all you can do with it is break it open, basically. So you basically always take the results of a line trace and feed it into break hit result, and it gives you a bunch of stuff. And so this is a really interesting and important thing to know about. So it tells you all sorts of information. Where was the hit? The impact point is, I think it's only used for complex traces. Maybe it's basically the same thing as location. Normal will give you the perpendicular vector to the point that was hit. So if you want to shoot a laser and have the laser reflect off the thing, you grab the normal out of it and you can reflect it around that point using maybe some of the matrix math we talked about earlier. This will tell you the material that was hit. So if, for example, you're walking on snow, sometimes you will have like footsteps that will crunch differently when you're on snow and things like that. It could be useful if you need to know what material was contacted. If it's a mirror, if you're in Portal, only some surfaces you can create a portal on. This is the actor we hit. This is very important. That's what we're going to be using in a second. And if you've got an actor that's got multiple components inside of it like this, you can actually grab, did I hit the head? Did I hit the arm? Did I hit their vulnerable areas? Which can crit or do double damage or whatever. If you've ever seen a lot of video games, bosses typically have body parts that flash or otherwise take extra damage, and that's how you do something like that. If it's a skeletal mesh, then you can grab the actual bone name. Did I hit their pelvis? Did I hit their clavicle? Did I hit their metatarsals? Whatever. And this is the starting point of the trace, which should be the same thing. And then that should be... I think these are just the same things here. Okay, and then time of impact. And so this is how far along the trace did we go. So if you guys have ever played, if you've ever played Overwatch, have you guys ever played Overwatch out of curiosity? Or any game that has damage fall off? So like if you shoot the pistols, Matrices pistols, they do full damage up to a certain range, and then they do less damage past that range. Have you guys heard of that term of fall off, damage fall off before? So originally I think the Matrices pistols did full damage at full range, and so like poor Farah would be like up hovering in the sky, and then McCree would go brrrr, and just like blow her out of the sky with his 6-shooter from like a quarter-mile away. And so they modified it so that he does full damage within kind of a medium range, and then after that the damage goes down. And so time here returns a value from 0 to 1 that tells you how far along in your trace line did it actually hit something. And so you could do something and say, well, if the time is less than 0.5, then do full damage. Otherwise, do some algebra and do lesser damage or something like that. Okay. Which is realistic due to bullet velocity loss. Sure. Yeah. Distance is how far away the hit was. So you don't have to do the vector length kind of thing there. You can just say like, okay, it was 500 meters away or whatever. So what I'm going to do here is I'm just going to pull out the hit actor, and I'm just going to get the name of it, get the object name or the display name. Let's do the object name. And we are just going to print this to the screen. And we're going to print the name of the, let's see, is that the right one? Display name's better. Okay, cool. We'll use the display name. Save, compile. And so now what will happen is when we shoot something, it will print guard cherry blueprint. Click the wall, wall 1. Click sphere 2. Click stair. Did it hit anything? Didn't hit anything. Doesn't have a name maybe. Big wall 2. Wall 3. So what it's doing, it's telling me the name of the object that I'm hitting. Editor cube 13. What a well named small statue number 2, editor cube number 8. Let's see if I can hit some of those barrels. I don't have enough range on it. It's only a 20-meter range. So get in there. There we go. Barrel 321. Barrel 197. Barrel 368. And so, let's see if I can hit any of these guys here. Landscape 5. Landscape 5. Landscape 5. And so the point is you can find out who it is you're hitting and do things like, say, like if I hit a person, do 5 damage. If I hit a demon, do 10 damage. You can do things like that. I don't actually care who I hit right now. I'm just going to be lit. So I'm going to get the location of the hit, and did it hit? True if there's a hit, false otherwise. Yeah, I should probably do that. So branch. So if there was a hit, then we will do fire emoji spawn emitter at location. So if there was a hit, we are going to, at what location? At this location. So at the location, the trace line hit something, we are going to spawn fire emoji. Oh, that's right there actually. Nice. Okay. Auto destroy when it finishes, and we could probably play a sound or something as well. Why not? Play sound at location. So at the location that the hit occurred, we will play Elven Harmonies now. Fantasy Adventure now. Fire Sparks. What does that sound like? No. Grenade? Sure, why not? Okay, this is going to be terrible because there's no cooldown on the attack. You guys see this? This is literally as often as I can click, it will play a sound and spawn an emitter. So get prepared for the spam. I should put in a cooldown thing, but I'm not. Okay. Voila. That's it. That's our class for today. You have any questions about this? Traceline is an amazingly versatile tool. Oops, did I screw it up? If I was doing this for realsies, I'd turn off the debugging lines, and I would add a cooldown to the attacks so that it can't attack as often as all that. And I'd get in more professional emitters that don't last forever, because this will tank your frame rate will go away, you know, if you keep spawning things and don't have them end, right? So there's obviously a lot that needs to be done, but that's the basics of like most of a game, right? Like that's most of how you interact with a game. You click or hit a keybind or something, and you know, hey, hello there, stay a while and listen. You know, that's it. That's the heart of what it takes to make most video games. You know, Traceline's one of your big tools. The other ones are touch, think, and radius. So super useful stuff. I will post this on to Discord, and your assignment for next time is to just copy what I did. Does that seem fair? It's not too complicated, I don't think. Just going to delete all of this stuff out. I don't need you anymore. We don't need animations. Spawn projectile. No. This is called laser fire. You think you guys can recreate this? Yep. All right. I will screenshot it for you. And as always, just create it in Unreal Engine, post a screenshot, have fun with it, right? Like, you don't have to just duplicate what I do. Like, what I'm trying to convey to you guys is I'm trying to give you guys the toolbox of, like, you know, the basics of what the components of making a game. And so this is a really, really important tool in your toolbox, which is line trace. So how do you select an object out of a world? By shooting a ray at it. Okay. And this stuff here is the linear algebra. Right? This is what I'm saying. Like, you can't make video games, as far as I can tell, without knowing at least some linear algebra. Yeah, creativity is a virtue. Have fun. You know, I award extra credit maybe if you do something cool. You know, put a mannequin into the world and talk to it. I don't know. Like, do something fun. Or you can just do this. It's up to you. Okay. So posting it in here, there is your example on how you can make a hit scan weapon, basically. The only other thing you'd want to do is damage the thing, right? Like, so if damage, right? Apply damage. So we should apply damage to the person we hit. And we will do 50 damage to them. There we go. Does that do anything? Nope, because there's no damage system in the game yet. But you know, there's no health on anything. But that's kind of, you know, what you do. Okay. And so that would make it if you hit somebody, then they take damage every time you click on them. Yep. All right, that's it for today, guys. Like, again, I can't overstate how important this tool is. This is like it's like being a carpenter. It's like your saw. Like, it's that important. You know, there's very few things that are going to be as important as this function right here. Okay. All right, so that's it for today, guys. Have fun playing Red Dragon. If you guys wish to incorporate me into your game, send me a message on Discord or Steam. I am terrible at it, so don't worry about me being good, because I'm not good at Red Dragon. And we will continue this discussion of how to make interactive video games, because that's what we're all about, next time. And then maybe we'll get into animations and things like that. Okay. Thanks, guys. Peace out.